This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, so we want to talk a little bit about the laws of nature and the form that the laws of nature take. Now, let me give you an example of a possible law of nature, which is not a law of nature, but discuss what's wrong with it. So here's a law of nature. Particles collide. Here's my axes, x and y, fixed and permanent on the blackboard, or fixed and permanent in space. And the rule is particles will collide and go off in weird directions whenever their x-coordinate is the same. Whenever the two particles, whenever their x-coordinates become the same, they suddenly turn around or go off in some other direction. So, for example, if this particle is moving this way and this one is moving this way, when they get to the same value of x, the rule is something happens. We needn't specify precisely what happens. Maybe they get turned around, or maybe they go off in some other direction. If they're moving like here's two other particles, they're moving in some other direction, not horizontally, but they're moving this way, that one's moving this way, and this one's moving this way. Again, the rule is whenever their x-coordinates become the same, they collide and go off and do something else. Well, that's a possible law of nature. It could have been like that. There's nothing mathematically inconsistent with it, but it just doesn't seem right. It seems to violate something that's deeply ingrained both in physics and the laws of physics and in our own intuition. What is it? What's the rule that's being violated? What? Homogeneity. Not homogeneity. No. It's, okay, good. It's not homogeneity. Homogeneity says that you can translate things and they'll stay the same, that the laws of nature are independent of where you put the center of your coordinates, and this is independent of where you put the center of your coordinates.
You didn't specify the x. Because you didn't specify the x.
Yes, I didn't specify the x. I just told you whenever x becomes equal, they collide. So we could say it this way. If we have two particles and they have coordinates, one called x1, and this is not the component of the coordinate, this is just labels which particle we're talking about. When x1 minus x of 2 become equal to 0, they collide. That's our rule. When the difference between the two x's are equal to 0, they collide. Well, that doesn't specify what particular value of x. It could be x way out here, it could be x way over there. They'll collide if we lift everything up vertically. They'll collide if we lift everything down vertically. So, in fact, it doesn't violate homogeneity of space. Space is everywhere the same in this rule. Yeah?
That means you can always find some coordinate where you can make them collide anytime you want.
No, but the rule here is they always collide, and if and only if their x's are equal. Right. This violates the isotropy of space. It violates the idea that when you rotate coordinates, the laws of physics stay the same. That the laws of physics are the same and independent of the orientation of your axes. Not the place where you put your origin, but the orientation of your axes. So, for example, if I reoriented my axes so that they look like, well, I'm going to reorient them so that this becomes the y-coordinate. Let's see, the y-coordinate now is over here, and the x-coordinate is over here. I'm simply relabeling. It is a rotation of my coordinates, a rotation by 90 degrees. Then exactly the same physics will require us to say that particles collide when the y's are equal. Different law, different form. If we oriented the axes in some awkward and arbitrary direction, then the law would become much more complicated. Some combination, they would only interact or they would only collide when some combination of the x's and y's were equal. So what would be violated here is the law that says the laws of physics are the same in every coordinate system, independent of the angles or independent of the angle of the x-axis. However, we do have to ensure that the coordinates are perpendicular to each other. There are things in the rules of physics which require us to use perpendicular coordinates to express the law. We can express the laws of physics in any coordinates we like, but they take a special and simple form in coordinates for which the axes are perpendicular to each other. Right? But the rule that says that it doesn't matter which way we orient our coordinates, it doesn't matter if I look at you this way or this way or this way or this way, the laws of physics should be the same. That's violated here. Okay. Let me give you an example of a law of physics which is not violated, which does not violate the rule that that laws of physics should be the same. Rotational invariance. This is called rotational invariance. Invariance under rotation of axes. Let's require that particles only interact if both the x coordinates of the two particles and the y coordinates of the two particles are equal. In other words, if x1 equals x2 and if y1 equals y2. What does that say? That says that the particles collide with each other, whatever it is they do. Maybe they turn around. I'm not going to specify exactly what they do. But the rule now would be they can only collide if they hit the same point. In other words, if both the x-coordinate and the y-coordinates are equal, then they collide. In fact, they don't even have to be moving along the same line. If a particle comes in along this axis and a particle comes in along this axis, and they find themselves at exactly the same point, then they collide. Right? That would be a law of nature that would be the same no matter how we orient our axes. If they collide when they come to the same point, then it doesn't matter whether we use this axis, whether we use this axis. And so this law of physics would be one which was invariant under rotations, would be the same no matter what orientation we chose for our axes. For the moment, I'm just ignoring time. For the moment, yeah, of course we do, but I was about to come to that. Okay. If there's a z coordinate, yes. If there's a z coordinate, yes. Right, so exactly so. And if space is three-dimensional, if z of 1 is equal to z of 2. If and only if these conditions are satisfied, then two particles will come to time in a minute. All right, we can re-express this in a single equation using vectors. We think of the position of a particle as a vector. Let's call that position r. I'll put a little arrow on top to indicate a vector, but now I mean a three-dimensional vector in ordinary space. No time for the moment. We'll come back to time in a minute. All right? We can write this as one equation. We can write it that the particle collides only if r1 is equal to r2, or r1 minus r of 2 is equal to 0. And this equation implies all components of r should be equal to 0. It's a vector equation. It's a vector equation. It has three components, and it's rotationally invariant. Okay. Here's a fact. If a vector is 0, and this vector is 0, this is the rule. Particles collide when a certain vector is 0. If a vector is 0, it's 0 in every coordinate system. In other words, if all components, a vector being 0 means all of its components are equal to 0. If all of the components of a vector are equal to 0, that's true in every coordinate system. If one or two components of the vector is equal to 0 and the other one is not, then that is not something which is true in every coordinate system. For example, here's a vector whose x component is equal to 0, right? In some other coordinate system, the x component of that vector is not equal to 0. So a law or a rule that would say this or that happens when a certain x component of a vector is equal to 0, that law will not in general be rotationally invariant. On the other hand, if we have a vector which is equal to 0, that means that it has no length at all, or that it's just a vector of 0 length, just the origin, then that vector is 0 in every coordinate system, no matter how we rotate it. That's why we express laws of nature in terms of vectors. That's why we choose to express them in terms of vectors. And the advantage of a vector description, vectors transform in a certain way. They transform when you rotate coordinates, the components of vectors change, they transform, but all vectors transform the same way when you rotate. So if a vector is equal to 0 in one frame, it's equal to 0 in another frame. If two vectors are equal in one frame, they are equal in any frame. And that's why we express, that is the reason that we express physics in terms of vectors, because we know that when we express it properly in terms of vectors, then the rules are independent of the orientation of our axes. Now, let's come to time. What about time? We could, let's let the horizontal axis be x again, but now let the vertical axis be time. X and t. Now, again, I could have a rule which says particles collide when, well, let's see. Particle collisions take place only when the time of the two particles is the same. What would that mean? That would mean that it's possible for two particles to collide. This indicates a particle going forward and then going backward. So it's moving along the x-axis, it's moving back along the x-axis. It's possible for particles to collide like that when the two times are equal. It's possible for them to collide at a later time, as long as the two times are equal. Collide means both of their velocities simultaneously change. Okay, that's what I mean by collide, that their velocities simultaneously change, but always at the same time. Okay? That's a perfectly good law of physics in Newtonian physics. And in fact, it is even a true law of physics in Newtonian physics. Well, it's a possible law in physics. Particles collide only, their velocities change simultaneously if they change at all. Okay? It's not a possible law in the special theory of relativity, and the reason is because of the idea of simultaneity is not invariant. So if I had a law of nature which said that two particles collide in one particular frame, in your frame, only when the times are equal, then in some other frame of reference, this frame of reference here, the times of collision would not be the same, and we would come to the conclusion that the relativity principle was not correct, that the laws of physics are not the same in all reference frames. There's one particular reference frame in which particle collisions take place at equal times, and in other frames of reference, it's some more complicated story in which some combination of x and t's have to be equal. All right, that's not the way physics works. The way physics works is Lorentz invariant. Lorentz invariant means, again, that the laws of physics are the same in all reference frames moving one with respect to the other. What does that entail about simple particle collisions, very simple particle collisions? Well, for a very simple particle collision, the simplest kind of particle collision, particles collide, they don't produce any other particles, not very much happens, they just bang into each other and they go off. That implies that collisions can only take place when the two particles find themselves at the same space-time point. In other words, not only when their times are equal, but when their positions are also equal. If two particles only collide when they're at the same event, the same point of space-time, then it doesn't matter which coordinates you use. Being at the same space-time point is an invariant concept. So that's a good law of physics from the point of view of relativity theory. The particles collide not just when they're at the same position in space, but also only at the same time. That also can be expressed in a kind of vector notation. If we represent the location of a particle, or a location of a point along a particle trajectory by a 4-vector, the 4-vector now has not only components x, y, and z, but it also has a component t. Then we would add in one more equation here, that the particles can only collide at an event, and that event has to have the same location in space and in time. Now you can say very much the same words about space-time that I said about space. If a vector in space-time has one or two or three components which are equal to 0, if a vector has space component equal to 0, that doesn't mean it's 0. It can have a time component. Here's a vector which has a time component but no space component. If I have some law of physics that says nothing more than something or other happens when the space components of a vector are equal to 0, that's not Lorentz invariant. And the reason is because in some other frame of reference, the x's of these 2 points are not the same. The x's of these 2 points are not the same in some other frame of reference. And so saying that something special happens when the x components or the y components or the z components of a vector are equal to 0, that can't be Lorentz invariant. The only Lorentz invariant statement that you can make concerning a rule about a vector is that all of its components have to be equal to 0. If in some frame of reference, if the law of nature is that some components equal 0, then it had better be all of them. Why? Because if you rotate or Lorentz transform your coordinates, you will find an inconsistency unless you require all of the components to be equal to 0. So, as I said, a law of physics could be that all 4 components of the location of 2 events. What are the 2 events? The 2 events are the sudden turning around of one particle and the sudden turning around of another particle. Those are both events. This law of physics would tell us that this event, the 2 events, could only happen if they were at the same space-time point. Okay? So we express laws of physics in terms of 4 vectors, or objects which transform in a particular coherent way. 4 vectors transform, the components transform into each other. We've seen, for example, that under Lorentz transformations, x and t, for example, get mixed up with each other. But they get mixed up with each other in such a way that if all the components are equal to 0 in one frame, then they're all equal to 0 in another frame. Right? So we express laws of physics in terms of objects which transform, and we always require either we transpose everything to the left-hand side and say that its components are a 4-vector, transform as a 4-vector, and must be equal to 0, or sometimes we might express the laws of physics as an equation with a left-hand side and a right-hand side, x of 2, y of 2, z of 2, t of 2. We express this particular form as expressing a certain rule by saying that 2 4-vectors are equal to each other. Not that some 4-vector is equal to 0, but a certain 4-vector associated with one event is equal to a 4-vector associated with the other event. So sometimes we express them by setting something to 0. Sometimes we express something by expressing a left-hand side equals a right-hand side. But the equations only make sense in this particular kind of case if they're whole expressions for entire 4 vectors, not just for pieces of the 4-vector. 4 vectors are, of course, things which transform under Lorentz transformations the same way that x, y, z, and t do. So let's define a 4-vector. It's an object with 4 components, one for each direction of space and one for time. And it transforms. What does it mean to transform? It means its value as measured in different reference frames transforms so that if I know it in one reference frame, I can give you the rule for computing it in another reference frame. For example, position, velocity, and so forth transform from one Lorentz frame to another. Position, we know how that transforms. Let's take the case of first the Lorentz transformation. There's x equals x minus vt. Y, this is x prime equals x minus vt over square root of 1 minus v squared. Incidentally, the notation, I keep writing square root of 1 minus v squared in the denominator here. There's a standard notation, gamma is equal to 1 over the square root of 1 minus v squared. Gamma of v. Gamma of v. It saves writing. There's nothing deep about it. It's just a way of rewriting. So another way to write this is that it's gamma times x minus vt. Okay, what else? Y prime. Say it again? Yeah. C is equal to 1. If we want to put C back into the formulas, we put it down here. All right. C is equal to 1. Y prime is equal to y. Z prime is equal to z. And T prime is equal to T minus Vx divided by root 1 minus v squared, or gamma times T minus Vx. This is the transformation properties of coordinates of an event. Okay. Other transformation properties involve rotations of space. Let me write down the transformations associated with rotations of space. Rotations of space are given. Here's an example. There are many, many axes that you can rotate about, but if I just rotate about the z-axis, vertically is the z-axis, I rotate my coordinates, x and y get mixed up with each other, z does not get mixed into it, and neither does time, if all I do is rotate my coordinate axes. Then the equations would look not totally dissimilar to this. Well, not totally similar either, but they would look like this. X prime is equal to x times cosine of an angle plus y times the sine of an angle. Let's put in here plus 0 times z plus 0 times t, just to remember that z and t are also part of the game. Y prime is equal to minus x cosine theta, no, minus x sine theta, minus x sine theta, plus y cosine theta, plus 0z plus 0t. Z prime is equal to z. I'm stacking things equal to z. I'm stacking things up so that x always appears in the same place, y always appears in the same place, z always appears in the same place. We would write 0x plus 0y plus z plus 0t. I'm being pedantic by putting in all these zeros here. And finally, t prime is equal to t, with all the others being 0. And so forth. This tells me how things transform under a rotation about the z-axis. This tells me how they transform under a Lorentz transformation. They're similar kinds of equations. In each case, they're linear equations of a form, of a particular form. A matrix is involved. If I wanted to write this in matrix form, I think I wrote that last time in matrix form. In each case, they're linear equations which have the form x prime mu. Now, mu goes 1, 2, 3, and 0. 1, 2, 3, and 0. 1 means x, 2 means y, 3 means z, and 0 means time. They're of the form x prime is equal to some matrix, mu nu, times x nu. For example, let me write down the matrix governing the Lorentz transformation. In that case, the matrix, let's make some notation. The first column will stand for x, the second column will stand for y, the third column for z, and the fourth column for t, or the 0th column. And same with rows, x, y, z. I'm just labeling now the entries. Okay, what are the entries here? Well, from here you can see that x prime is equal to gamma x. So there's a gamma over here. There's a minus v gamma over here, and a 0, 0. That indicates that y and z don't come into this equation, but there's a gamma x and a gamma vt with a minus sign. And so on. Let's see, y prime, that's equal to 0 times x plus 1 times y plus 0 times z plus 0 times t. Same with z, 1, 0. And t prime, that's equal, that has a minus v gamma here, 0, 0, and gamma. That's the matrix which governs the simple Lorentz transformation here. The matrix which would govern a rotation of space would also be a matrix with 4 by 4 structure, but here I can just read it right off here. The corresponding matrix for a rotation about the z-axis. A rotation about the z-axis would look like cosine theta, sine theta, 0, 0, minus sine theta, cosine theta, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That would be the matrix which represents a rotation. Now, you can combine these transformations together in a wide variety of ways by mixing up rotations and Lorentz transformations. For example, if I wanted to do a Lorentz transformation along some different angle, let's say an angle in the xy plane, then first I would make a coordinate transformation that turned the x-axis into the new x-axis. I would use the rotation matrix here to find new coordinates along which the new x-axis is along the direction that I want to do the Lorentz transformation. Then, after having done that, I would do a second transformation, which would be a Lorentz transformation between time and the new x-axis. That would entail multiplying these two matrices together, basically. That's what the matrix for the full rotation would be, is it would be the product of the full Lorentz transformation, or the full combination of Lorentz transformation and rotation would involve the product of these. But really, it's enough to know that physics is invariant under rotations and know how to write the rotation matrices, and invariant under Lorentz boosts along, this is called a Lorentz boost. Boost means you speed up the velocity. It's enough to know those two forms here and know that you mix them up in all kinds of ways to do more general Lorentz transformations, more general transformations. Well, you get different answers. You get different answers. Yep. If you first Lorentz transform, let me show you why. Imagine your first Lorentz transform, okay? So that brings you to a new coordinate frame in which this is the new space axis here, all right? And then you do your rotation. Your rotation is a rotation about this plane here, not this plane. So it depends on the order. If you first Lorentz transformed and then rotated, you would be rotating about a different surface. You would be rotating a different surface than if you first rotated and then Lorentz transformed. So the order of action does matter. But it's enough to know these two and how to combine them to know how to do any transformation of the kind that applies to vectors. All right, so the more general statement is that there's a matrix of some sort. The matrix has to satisfy some rules. All right, but basically the rules are that it's various kinds of products of these matrices. And we just write it in a general form that the primed coordinates are some matrix times the unprimed coordinates. And for each specific situation where we want to transform from one coordinate system to another, we have to know what the matrix is, but usually we can figure that out. We can also write this in the form a column vector, x prime, is equal to a matrix. Now let's just think of that as a matrix now, times a column vector x. Just think of it as matrix multiplication or manipulation of indices. Remember, I want to remind you one thing. When you have repeated four-dimensional indices like this, particularly when one of them is exhibited as an upper index and one of them is exhibited as a lower index, repeating the indices means sum over the indices. It's the same summation that you would do if you multiplied the matrix, or let's put it x1, x1, x2, x3, x0. All right? When you work out the components of the product, you have to sum gamma times x prime plus 0 times x, gamma times x1 plus 0 times x2 plus 0 times x3 and so forth. That's the same sum that's implicit here in summing over the repeated index. All right, so this is just a notational device for writing out generally what a Lorentz transformation does. It's a linear operation like that. That's a special case. This is a special case of the transformation of vectors where the vector in this case happens to be the space-time position of a point. There are other four vectors. There are other four vectors which are interesting. For example, the four vector associated with velocity. We'll come back to it. The four vector associated with proper velocity. Remember what proper velocity is. Proper velocity is not dx by dt, but it's dx mu by d tau. Tau is proper time. First of all, before we even go ahead, even before we talk about four vectors, we should talk about scalars. Scalars are things which are the same in every reference frame. For example, if we're talking about only rotations, let's forget for the moment Lorentz transformations, just rotations. Right? The temperature at this point right over here is the same no matter which way we orient our axes. So temperature is a thing which doesn't transform under rotations in any case. Temperature is a scalar. It's a scalar quantity, which means it doesn't have components. It's just one number characterizing it. And the temperature of a point in space doesn't depend on what axes are used to describe it. How about the distance between 2 points? The distance between 2 points. Now, I'm not thinking about space-time. I'm thinking only about space. The distance between 2 points, it doesn't matter which way I turn my head. The distance between them, the number of inches between these 2 points, is the same no matter which way I orient my axes. So distance is also a scalar quantity. Components of vectors are not scalar quantities. They change from one reference frame to another, but the distance between 2 points is a scalar quantity. Right? I might have not a law of nature so much, but a simple claim. I might tell you, for example, that the distance between 2 points measured in meters happens to be the same as the temperature measured in Fahrenheit. Right? It's a stupid thing, but it might be. I mean, it might be. What is the temperature in Fahrenheit in here? About 70 degrees? Yeah. All right, so I can imagine 2 points separated by 70 centimeters. And then I would tell you, it just so happens that the distance between my fists, measured in centimeters, happens to be the same as the temperature in the room. Does that depend on which axes I use? No, because the distance between the points doesn't depend on the axes. The temperature doesn't depend on the axes. They're both scalar quantities. And so the statement that the temperature equals the distance, that's a rotationally invariant statement. And if it's true in one frame, it will be true in every frame. In this case, it's a statement about scalar quantities. I should have talked about scalars even before I mentioned vectors. Vectors are more complicated. For vectors, if a thing is true, it better be true for all components of the vector. The thing is true in every frame of reference. All right, now, this is a 4-vector. And the meaning of saying it's a 4-vector is, first of all, it has 4 components. But let's call it, well, let's just call it the general 4-vector, not this specific one, but the general 4-vector. Let's call it for the moment A mu. This one is usually called U mu. But let's just generalize and think about the general notion of a 4-vector, and let's call it A mu. Its components are equal to A1, A2, A3, and A4, or A0, sorry. The definition of a 4-vector, and it does apply to the 4 velocity, or the proper velocity, the definition of a 4-vector is it's a thing which transforms. Again, transforms means that if you know it in one frame, you can determine it in another frame. The definition is that it transforms exactly the same way as x, as the components of x. So if I know A in one frame, in another frame, in the primed frame, the components A prime mu are equal to L mu nu times their values in the first frame. Exactly the same as x. For example, the 4 components of A, if I just did an ordinary Lorentz transformation, would vary in exactly the same way as x, y, z, and t. I won't bother writing it down. The transformation properties of a 4-vector are the same as x, y, z, and t. That's the definition of a 4-vector. If a 4-vector is 0 in one frame of reference, if this is 0 in one frame of reference, it's obviously 0 in every frame of reference. Just if every component is 0 here, then every component will be 0 here. If 2 vectors are equal in one frame of reference, then they will be equal in every frame of reference, assuming all 4 components are equal. So that's the value of thinking in terms of 4 vectors. The things which are true in every frame of reference. This makes them useful for describing the laws of physics, which are supposed to be true in every frame of reference. Now, representing a vector in this form here is called the contravariant form of the vector. There is another form for the same vector, which is called the covariant form, or the covariant components. It's really imagined to be the same geometric object, just described in a different way. And to describe it, we put the mu downstairs. It's upstairs, downstairs. And what it is it's the same collection of components, exactly the same, except the space components, 1, 2, and 3, are changed in sign. A1, A2, A3, minus, minus, A0. Why on earth would I want to do that? Well, first, before why I want to do it, let me just describe it mathematically a little bit differently. Here's the mathematical connection between the two. A mu is equal to a certain matrix. I'll write down that matrix in a moment. Mu nu times A nu. Now, before we do anything else, let's look at this equation before I even say what it means. It has the nice feature that it's first of all summed over the new index. Always when you sum over an index, it had better be one downstairs with one upstairs. Otherwise, you're writing something that doesn't make sense. Now, you can't, so far I haven't even told you what this means, so whether it makes sense or not, I'm just telling you now for future purposes. If you're writing out some equations like this and you discover that you're summing over indices, both of which are upstairs or both of which are downstairs, you made some mistake. Okay? This is the nice form that Lorentz invariant equations should take. Summing over indices should always be one up and one down, but you'll understand why in due time. But let's see what this means. Let's see exactly what this means. First of all, what is eta? Eta is a matrix, and it's the matrix minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, plus 1. What does it do when it multiplies a column? Here's a column, so let's put the column there. Let's multiply eta by mu, by A. Eta times A, thought of as a matrix, times a column vector A. That we just get by writing down A1, A2, A3, and A4. And let's see what we get. Forget the left-hand side here. Just let's look at the product. It gives us minus A1 in the first entry, minus A1, minus A2, minus A3, plus A naught. This should be naught. Right. Minus 1 times A1 plus a bunch of zeros, minus 1 times A2, a bunch of zeros, and so forth. So you go between the covariant form and the contravariant form by multiplying by this matrix eta. It's a convenient notational device. Why do we do it? Yeah.
In your last column vector, that should be negative 2 upstairs when you're getting confused.
Yeah, good, thank you.
In the equation above it, a lower mu, the indices on the component should be upstairs.
You're absolutely right. And in fact, we could identify this with A1, A2, A3, and A0, where these are lower indices. You're absolutely right. That was not consistent. Thank you. Okay, why would we want to do this? We want to do this because it's a useful trick in forming scalars, invariants, things which don't change under coordinate transformation. For example, supposing I take A mu and I multiply it by A mu downstairs. Again, summed over indices which are repeated. What does this mean? This means we can read it directly off here. It's A1 upstairs times minus A1 upstairs. So this is just A1 squared plus, no, minus A1 squared minus A2 squared minus A3 squared plus A4 squared. Well, this is very much like taking the x vector and computing the proper length or the proper time associated with the x vector. if we go back to the x vector here, we remember that the difference of the time squared components and the space squared components are what we called tau, tau squared. Tau squared was the difference of these components. And the main feature of it was that it didn't change from reference frame to reference frame. It was invariant. Well, since the a's, by definition, transform exactly the same way as x's, it follows that this quantity does not change under Lorentz transformation, or rotation, or any other kind of transformation of the kind we're dealing with. This is an invariant, or a scalar. So, just as a notational trick to write in a compact way a1 squared, well, minus a1 squared, minus a2 squared, minus a3 squared, plus a4 squared, we invent the notation with a lower index and an upper index, where the lower index changes the sign of all three space components and leaves the time component. I keep writing a4, but I mean a0. So that's just a trick to keep track of this minus sign in multiplying vectors to form Lorentz invariant scalars. For example, in this language, we would just write that the proper length of a vector x is x mu, and this would stand for t squared minus x squared minus y squared minus z squared. Okay? So that's the notational trick to keep track of minus signs. And this eta matrix here is part of that notational trick. It's just another compact way of writing that the thing with the lower components is the thing with the upper components with the appropriate sign changes made. Yeah.
That might look like it was a column vector times a row vector, but we're looking at this more as just an inner product, so you don't worry about with the upper mu first.
Say it again. Oh.
It looks like column vector times row vector instead of row vector times column vector.
Am I writing it wrong? I always think of this as column. This is matrix. And this is also column.
Oh, the lower mu is also considered.
It's also a column, yeah, but both should be thought of as columns, yeah. This is not going from columns to rows. Well, in some sense you can think of it that way, but I wouldn't, not now. Just think of them as rows. Sorry, as columns. Another way to write a mu, which is the invariant, is to write eta mu nu, a mu, a nu. Why is that? Because if I multiply eta mu nu by a mu, well, let's change to nu. When you sum over an index, it doesn't matter what you call it. All right. So this lowered the index of a, and then multiplied it by the contravariant a. All right, so we have various ways to write the same thing. No, the order doesn't matter. No, the order doesn't matter. It's diagonal. First of all, it's symmetric. Yeah, the order doesn't matter. Even if it wasn't symmetric, the order wouldn't matter. No, the order does not matter. Not until we start doing quantum mechanics anyway, which we're not going to do. Okay. Let me prove something else. Suppose you have two 4 vectors. Let's call them A and B. A mu, B mu is, of course, exactly the same thing, incidentally, as A sub mu, B super mu. Why is that? Well, both of them are just A naught, B naught, minus A1, B1 minus A2, B2, minus the same thing for 3. It doesn't matter if you put the upper index on A and the lower index on B, or swap them. Lower index on A, upper index on B. Same thing. You get the same thing. So basically, the product, we could just think of this as a new kind of product of A times B for two 4 vectors. It's not the product of two numbers, it's the product of two 4 vectors. And the product of two 4 vectors, the only thing new about it is that this eta is in there, this funny sign business. Otherwise, it would be very much like the dot product of ordinary vectors. Now, what about this object here? Is this object invariant when you have two different vectors? If you just have one vector, A, and it transforms under Lorentz transformations, then this particular combination doesn't change as you go from frame to frame. What about if you have two vectors, A times B? That also is invariant. There's a simple way to prove it. If A is a 4 vector and B is a 4 vector, then A plus B and A minus B are both 4 vectors. That means that A plus B times A plus B, these are both 4 vectors, A and B are 4 vectors, A plus B is a 4 vector, and now when I write product, I mean product in this sense, one upper and one lower, but it doesn't matter which one is upper and which one is lower. This must be invariant, because if A and B are 4 vectors, so is A plus B. So this is invariant. What about the difference? A minus B times A minus B. That's also invariant, because if you have two 4 vectors, the difference between them is another 4 vector. Well, this is A squared, this is A times A plus B times B plus twice A times B. This is A times A plus B times B minus twice A times B. If both of these are invariant, then it had better be that A times B is also invariant. Why? Because if you subtract these, the A squares will cancel, the B squares would cancel, and you'll just get twice A times B. Twice A times B is also invariant. So anything with one upper index like this and one lower index, combine them together, you form an invariant quantity which is the same in every reference frame. Now, of course, it's good to find things which are the same in every reference frame, because a law of nature is supposed to be the same in every reference frame. Or a measurement of a distinct quantity should be the same in every frame. Temperature, distance between particles, whatever. All right, let's go on to consider some specific 4 vector, the velocity 4 vector, which we did last time, but now armed with some powerful notation, let's define some things. If we have a world line of a particle and we have two neighboring points, then the separation between them is a little infinitesimally small 4 vector, and we can write it as dx mu. All right. It has, let's just write what its components are. Its components are dx, dy, dz, and dt, or equivalently dx1, dx2, dx3, and dx0. That's a component, that's a 4 vector. Right? It's infinitesimally small. If we divide that by d tau, and let's work out what d tau is. D tau squared, the square of d tau is dt squared minus dx squared minus dy squared minus dz squared. But that's just dx mu dx mu. dt squared minus dx squared minus dy squared dz minus dz squared is d tau squared, or d tau is just the square root of this. Dx mu divided by d tau, okay, So this is the rate of change of the x coordinate, of the x mu coordinate of the particle, but not rate of change with ordinary time, but rate of change with proper time. The rate at which the coordinates of the particle are changing, but as measured by a clock moving with the particle. That's the x mu d tau, and that is called the proper force velocity, u mu. What are its components? Well, we can, before I talk about the components of it, yeah, this is the force velocity. Notice it has 4 components. That's weird. You would think that if you know the 3 components of velocity, that you know everything about how the particle is moving, and that's true. And the reason is because the 4th component of the velocity is determined in terms of the first 3 components. Why is that? That's because this velocity here satisfies a constraint, satisfies a relationship which allows you to compute the 4th component from the first 3. Let's see what that constraint is. I maintain that this object here is a unit vector. What does a unit vector mean for a 4 vector? It means that its inner product with itself, or that u mu is equal to 1. It's kind of like a unit vector in ordinary space. If you have a unit vector in ordinary space and you know its x component, then you also know its y component, up to a sign. There's an ambiguous sign. All right? Why? Because the sums of the squares of the components must equal 1. Well, the force velocity is a unit vector. How do we see that? Let's just check that. Let's just check that. All we have to do is work it out. dx mu, this is equal to dx mu by d tau, dx mu by d tau. Right. Upper component, lower component. But look here, d tau squared is just dx mu. That's what we have in the numerator. So the numerator and the denominator are the same thing. dx mu is d tau squared. In the denominator, you also have d tau squared. And so the force velocity is a kind of unit 4 vector. The 4 components of the force velocity are not independent. The 4th component, apart from an ambiguous sign, is completely determined in terms of the other 3 components.
For speeds much less than c, does the force velocity become similar to regular velocity?
Yes, let's do that right now. We did it last time, but I'll remind you. That was exactly what I was about to do. So let's do it. Let's do u1, u2, and u3. All right, just the x and y and z components. Let's just call it ux. When I'm thinking about space, for some reason, I rather think about x, y, and z than 1, 2, and 3. But let's say u sub x, or u super x, is equal to dx by d tau. But that's the same as dx by dt times dt by d tau. So we need to know, what is this, of course? This is just ordinary velocity. Okay, we can do the same thing for the y component. This is equal to dy by dt, dt by d tau. Same thing for uz. Is equal to dz by dt, dt by d tau. So for the space components here, we can just write a simple equation. We can write one equation. We can write that u, thought of as an ordinary 3-dimensional vector, is equal to ordinary velocity, let's just call this ordinary velocity, times dt by d tau. That's true for all 3 components. We'll worry about the 4th component in a minute. We'll come to the 4th component of u in a minute, but let's just take the first 3 components. The relation between the ordinary velocity and the proper velocity is a simple factor, dt by d tau. Let's work out what that is. Let's work out what dt by d tau is. D tau is equal, now I'm going to write it out explicitly, dt squared minus dx squared minus dy squared minus dz squared. D tau squared. Sorry, that's d tau squared, so it's the square root of this. Let's leave it this way, d tau squared. Now what we want is dt by d tau, the ratio of dt and d tau. Let me divide this by dt squared. dt squared, dt squared, dt squared, dt squared. Okay. Well, this is easy. This is just 1 minus v squared. This is equal to 1 minus the velocity squared. The velocity of the particle. Now, we're not talking about velocities of two frames of reference necessarily. We're really just talking about the velocity of a particle. And to indicate that it's a three-dimensional velocity, ordinary velocity, I'll put a little arrow on top of it to indicate ordinary vector. 1 minus velocity squared is dt by d tau squared. Sorry, d tau by dt. So all I have to do in order to compute dt by d tau is turn it upside down and take its square root. So dt by d tau, that's equal to 1 divided by the square root of 1 minus v squared. That's what we called gamma up there. It's just gamma of v. It's the same gamma. But now it's associated with the velocity of a particle. And it's the full velocity, all three components of it squared. All right, so now we know the relationship between the four velocities, or the first, these are the three components of space of the four velocity and the ordinary velocity. Let's just write down what it is. There's a 1 divided by square root of 1 minus v squared, and let's put in c squared now. C squared would go over here. Question?
Yeah, that second part there, the dx squared, dt squared.
This is not second derivative. This is the square of the first derivative.
Okay, because when I do velocity squared, I get all sorts of cross terms.
You do velocity squared.
Dt
No. Wait.
dx dt plus dy dt plus
Whoa,
dc squared.
what are we doing? What are we doing? We calculated, no, let's do it again. This is definition, d tau squared. Definition of d tau squared is dt squared minus dx squared minus dy squared minus dz squared. That's definition of d tau squared. Okay. Now we're just dividing it, and it's a square of something. It's not the second derivative of anything. It's just a square of d tau squared. We divide that by dt squared. dt squared by dt squared is just 1. dx squared by dt squared is the x component of velocity squared. So this is minus vx squared.
Okay, by squaring a vector, you mean dot product of it.
Well, that was definition. Actually, I didn't even, yes, but I didn't even really use it. I just used the definition of what I meant by d tau squared. But it just was, as you said, the dot product squared. Yeah. Okay, so there we are. We have, this is the space components of the four velocity. And all you do is multiply the ordinary velocity by a number which is very, very close to 1 if the velocity is much smaller than c.
So I'm a little confused at this point. Because I was not thinking of that v as the relative velocity between two coordinate frames.
It's not now. It's just the velocity of a particle in some particular frame.
So it kind of looks.
It's the same. It's a similar mathematical expression,
So I could
but yeah.
fall into that trap.
Yeah, you could, I tried to steer you out of that by saying it's not the velocity of another frame. Yeah, right. Right, but no, let's say it even again. Right. This gamma of v here is a particular function of the magnitude of a velocity, any velocity. If it happens to be the velocity of a particle, it's velocity of a particle. If it's the velocity of a moving frame, it's the velocity of a moving frame. But its definition is 1 divided by the square root of 1 minus v squared. That's its definition. Where v squared here means the square of the magnitude of the velocity, ordinary velocity squared. The same velocity that if you were to write the kinetic energy, it would be 1/2 mv squared. Same velocity squared here. Okay, so if it's a particle, we put in its velocity. All three components, we sum them and square them, and that defines this quantity here. It also happens to be the same mathematical expression that goes into the Lorentz transformation. It's not completely accidental, but at this point it's just a notation for a particular function. Okay, so this is the first three components of u. What about the fourth component of u? The fourth component of u is by definition dt by d tau. Well, it's dx naught by d tau, which is the same as dt by d tau. And that is just 1 divided by square root of 1 minus v squared over c squared. That's what dt d tau was. All right, so we now know what the four components of u are in terms of the ordinary velocities. Okay? First of all, they're bigger than the ordinary velocities. 1 minus v squared over c squared is always less than 1. 1 over it is greater than 1, and so forth. So the space components of the velocity are always bigger than the component of ordinary velocity. Notice something very strange happens when the velocity gets to be up near the speed of light, ordinary velocity. When ordinary velocity approaches the speed of light, u grows enormous. So 4 velocity gets hugely big when the ordinary three-dimensional velocity gets near the speed of light. What about the fourth component? The fourth component, if the velocity is small, is essentially 1. The fourth component is just the number 1 in the limit that the velocity is small. When the velocity gets big, or gets up near the speed of light, then u naught also gets big.
Doesn't u not need the units of velocity?
What's that?
Doesn't u not need the units of velocity?
Well, don't forget that we set the speed of light equal to 1. So we've lost that particular fact. We could multiply it by velocity, the speed of light, and give it components of the velocity. If we wanted it to have, if we wanted it to have units of velocity when the speed of light was not equal to 1, we would multiply it by c. And that's fine. You can do that if you like. You just have to remember what you're talking about. It's more usual to think of the fourth component of the velocity as something near 1. But you can think of it as being near c. Now, that brings us to the 4 components of momentum. Let's talk about a particle. It doesn't have to be a particle. Any object that has a certain rest mass, we'll call the rest mass m, then it has 4 components. It's also a 4 vector. Momentum is standard notation for it is to call it p. That's true in Newtonian mechanics. It's true in relativistic mechanics. Momentum, the symbol is p. Now, in non-relativistic physics, it's just m times v, mass times velocity. But that's not a very good 4 vector. Mass times ordinary velocity, it's not a 4 vector. If we want to make a 4 vector out of it, because we're going to want to write equations which make sense in every reference frame, then we want to take it to be mass times u mu. Right? That's, of course, mass times v mu divided by square root of 1 minus v squared over c squared, but I won't bother writing the c squared now. So that's a definition, if you like. This is the definition of the momentum of an object of mass m moving with velocity u, moving with 4 velocity u. And it has 4 components. The first 3 components are very close to the ordinary momentum when the velocity is small. The last component is the energy. I showed you that last time. It's essentially mc squared plus 1/2 mv squared, and I'll come back to that. We'll come back to that. But let's just note that this is the definition of the 4 components of velocity, momentum. All right, the law of physics that we're going to study, I think we may actually get to it tonight. In fact, I think we might actually be there, about to start it anyway. No, v is not a 4 vector. Right. I did. It does have 4 components, though, one of which is just 1. Let's just get rid of this side of the equation, not get ourselves confused. Right. All right, what we're going to do now is we're going to take a bit of a vacation from relativity, and we're going to write the law of motion, the ordinary laws of motion, even before relativity. They're going. Noisy little bastards. Excuse me. P mu equals, yeah. All right. Now what I want to do is pick a law of physics, an important law of physics. Think about it from the point of view pre-Einstein, and then try to figure out how we would redesign it, change it, modify it, so that it would become a relativistically invariant law of motion. It's the law of motion of charged particles in electric and magnetic fields. Now, I'll tell you right now, the decomposition into electric and magnetic is not an invariant decomposition. What in one frame of reference is a magnetic field may become a combination of electric and magnetic in another frame, and vice versa. So I want to write down first the pre-Einstein law of motion of a particle, charged particle, in an electromagnetic field. And then we can try to think, how do we modify this in order to make it a legitimate relativistic equation that will be the same in every reference frame? As I write it, it will not be the same in every reference frame, because it will be based on pre-Einstein physics. And the fact that it's not the same in every reference frame is one of the things that really led Einstein to say something's wrong with ordinary kinematics, with ordinary space, time, and motion. All right. Here's our law. First of all, F equals ma. Force is mass times acceleration. Now, we haven't even talked about acceleration, but I think we can guess the rule for what relativistic acceleration is. If ordinary acceleration is the time rate of change of velocity, then I don't think it would surprise you very much at this point if I told you that the four-dimensional acceleration is the proper time rate of change of the four-dimensional velocity vector. Remember that the first three components of u are very close to the ordinary velocity, and tau is very close to ordinary time for slowly moving objects. So for slowly moving objects, the first three components are very close to the acceleration, ordinary acceleration. But we'll come back to this. For the time being, let's just think about ordinary acceleration, the old-fashioned kind. F equals ma. All we need to know in order to write down Newton's equations for the motion of a particle is what the force on it is. The force of an electric particle, of an electrically charged particle, the force on an electrically charged particle, is made up out of the electric field, which is a three-vector, meaning to say it has three components, x, y, and z. Something not good about that. And also the magnetic field, which also has three components. Something not good about that too, I mean, because after all, we want to write things in terms of four-dimensional objects, not in terms of three-dimensional objects. So there's going to be something quite not right about what we're going to write down, at least until we learn to understand better the relation between electric and magnetic fields. But for the time being, let's just write down the force law, and here it is. This is Lorentz's force law, discovered by Lorentz sometime around, I don't know, 1895. Of course, it was always known that it was proportional to the electric charge. It was known that this is acceleration. Everything is an ordinary three-dimensional vector here. There was charge times electric field. That goes back to who? Who was the first one who wrote down charge times electric field? Faraday. Faraday first had the idea of electric fields. If you put charges into electric fields, forces are exerted on them. And then plus, also charge, times the velocity cross the magnetic field. Okay, now I have to tell you what the cross product is. Anybody not know what the cross product is? Okay. In a moment, anyway. This piece of the force is called velocity independent. There's no velocity in here. There is a velocity in here. Okay? But remember, velocity, what in one frame of reference a particle may have, let's suppose there was no electric field altogether. Okay? But because the particle is moving with a velocity in a magnetic field, there's a force on it. Okay? That's interesting, because in some other frame of reference, the velocity may be zero. If the velocity is zero, then there would be no contribution to the force from here, but there's a force on it. We've just seen there's a force on it. The force on it makes it accelerate. If it accelerates in one frame, it accelerates in every frame. Or another way to say it is if it doesn't accelerate in one frame, it doesn't accelerate in another frame. And so something's funny here. If there was only a magnetic field, then in some other frame of reference, there would have to be an electric field. Okay? In a frame of reference in which the velocity of the particle was zero, a frame moving with a particle, that force could only come from the electric field. So that immediately tells us that electric and magnetic fields have to mix up with each other when you do Lorentz transformations. Right? What is the connection between electric and magnetic fields? And the connection is that the two of them together form a new kind of object which we haven't written down yet. It's called a tensor. Here's an object which has 6 components altogether. It's surely not a scalar. It's got components x, y, and z. B also has components x, y, and z. It doesn't have 4 components. It has 6 components altogether. So it's not a 4-vector. It's something new. Right? It's got to be something new. And moreover, these things transform into each other under various kinds of Lorentz transformations. That's what we know. So the next question is, what kind of other objects are there that we can define besides scalars and vectors? And the next class of objects is called tensors. In order to write down what the electromagnetic field is from the point of view of relativity, we have to understand tensors. Tensors are the new ingredient. Well, let me tell you, first of all, the simplest way to think about a tensor. I'm going to call tensors T, capital T. A scalar is a tensor. It's called a tensor of 0 rank. It has no indices. Why does it have no indices? Because a scalar has no indices. A scalar doesn't have any components. So a scalar is the simplest kind of tensor. A vector, a 4-vector, is also a tensor. Okay? But it's a tensor of rank 1, which means it's an object which has only, well, let's call it A. A mu. It has only one index. It has 4 components, but it has only one index. That index can run over 4 different values. A tensor is a thing which has 2 indices. The simplest tensor is to take 2 vectors. Let's call them A and B does not stand for the magnetic field now. Okay? Maybe I should call it C. I'll call it B. All right? Take another 4-vector and put them next to each other. There's an object. It's an object which has how many components altogether? It's got 16 components altogether, right? 16 components because A has 4 components, B has 4 components. Mu and nu each can be anything from 1 to 4 or from 0 to 3. And so altogether there are 16 components. We could display these 16 components as a matrix, as a 4 by 4 matrix. In the first place, we would put let's say A1, B1. Then I think it's A1, B2, A1, B3, A1, B0, and then A2, B1, and so forth. We could display them, all 16 components, just lay them out on a grid and draw a matrix for them. That's the simplest form of tensor, just to take 2 vectors and juxtapose them together, take all 16 components, and those 16 components form an object which is called a second-rank tensor. You could take 3 vectors, take a 3rd vector. Now we would have to make a cube to represent it. Let's take first of all, this is a second-rank vector, sorry, a second-rank tensor. Don't worry about why it's called a tensor. I mean, is it nervous? It's not nervous. It's not the. Actually, it does come from the word tense, but not the. It's not nervous. It just has 2 indices. Right? Second-rank tensor. Of course, we can construct 3rd-rank tensors. A 3rd-rank tensor would be made out of 3 vectors: mu, nu, sigma, let's say. Okay? That would be a 3rd-rank tensor. How many components does it have? 4 times 4 is 16, 64 components. And if we wanted to display them, we might display them on as cells in a cube. And thus it goes. We could have 4th-rank tensors, 5th-rank tensors. Now, what is it that characterizes a tensor? Is it just a product of 2 vectors? No. It's any object which transforms the same way as a product of two vectors. All right. So let's ask how a product of two vectors transforms. The product, all 16 components. Supposing we know the components of A, then the components of A prime in another frame of reference are by definition L mu nu A nu. That's the transformation property of A. It's also the transformation property of B. B prime mu, let's use a different variable, sigma, is equal to L sigma tau A tau. All right, remember, it doesn't matter what you call the summation index. I call this one nu and I call this one tau, but on the left-hand side I have an open sigma index, which means this really does correspond to some particular component, and we have a sigma on this side. All right, what's the transformation property of A prime mu B prime sigma? That's the primed component, the mu sigma component of the primed tensor. Prime means its components in the primed reference frame. Well, it's very easy. Just L mu nu L. Yes. A nu B tau. All right, so whatever a tensor is, it transforms with an object which has two L's in it. One for each index. Here's the mu index, here's the sigma index. Notice that the lower component of this L goes with A, the upper component of this L also goes with A prime. The lower component tau goes with B, the upper component sigma also goes with B, B prime in this case. Now I can tell you what the general law of a second-rank tensor transformation is. The general law is take a tensor in the primed reference frame is given by exactly the same kind of structure, L mu nu, L sigma tau, T nu tau. Okay, so here's the rule. If you know the components of T in one frame, the unprimed frame, then you take the L's, the Lorentz transformation matrices, and you simply apply them. The nu index transforms into the mu index by the mu nu matrix. The sigma the tau index becomes the sigma index by L sigma tau. Okay. So you see the pattern. This pattern repeats itself. If there's a third-rank tensor, then there's just one more L, making it transform just as if it were the product of three vectors. This is what is called a tensor. You can't ask me why that's called a tensor, and you can't ask me why I wrote it down. All you can say, is it useful? Is it useful to define it? It is very useful to define it, but here's its definition. It's a thing which transforms as if it were the 16 components of the product of two vectors. Now, there are other things. It doesn't have to be the product of two vectors. For example, here's something. Take A mu B sigma. That's not the same as A sigma B mu. It's not the same thing. If, for example, I take the 1,3 matrix element, the 1,3 matrix element of this will be A1 B3. The 1,3 matrix element of this, or the 1,3 component of this, will be A3 B1. So they're not the same thing, A mu B sigma and A sigma B mu. But both of them transform as tensors. You could add them. The result is still a tensor, but it is not an object which is just the product of two vectors. You could do other things. You could take some third vector, and you could add some third and fourth vector, and add it, C mu d sigma. C mu d sigma is a tensor. If you add it to some previous tensor, it is still a tensor, still transforms the same way. So not every tensor is just a product of two vectors, but every tensor transforms the same way as a product of two vectors. Now, there are two special kinds of tensors of rank 2. Rank 2. All right? The two special kinds are called antisymmetric and symmetric. An antisymmetric tensor is one that has the property T mu nu equals T nu mu. This is symmetric, sorry. That's symmetric. That says that T12 equals T21. Symmetric, it doesn't, in this case, it doesn't matter which order you put the indices. That's called a symmetric tensor of rank 2. An antisymmetric tensor of rank 2 is one which changes sign when you flip it. In terms of matrices, they correspond to symmetric and antisymmetric matrices. So if we take a symmetric tensor and we display its all 16 components of it, then it will have the property that it will be symmetric. The 1, 2 element over here will be the same as the 2, 1 element over here. The 1, 1 element will be whatever it is. The 2, 2 element will be whatever it is. But then T1, 3 will equal T3, 1. T1, 3 will be the same. So the matrix will have a symmetry. It'll be a symmetric matrix, which means that the components off the diagonal will reflect into each other. That's a symmetric matrix. But more interesting for us today and the next time is going to be the antisymmetric matrix. What about the antisymmetric matrix? That has the property, when you reflect it, it changes sign. T13 is minus T31. What about T11? It's got to be minus T11. All right? T11 must be minus T11. Well, if T11 is minus T11, then the antisymmetric matrix must have zeros on the diagonal. Zeros on the diagonal. And then off diagonal it has T12, T13, T10. Let's do it nicely. I'm going to make a nice big matrix, and I'm going to subdivide it into 4, and I'm going to subdivide it into 4, and then its components. This is an antisymmetric tensor. Its diagonal elements all have to be 0. That's because T11 must equal minus T11. On the other hand, T12 has to equal minus T21. So T12 up here and minus T12 over here. This is minus this. T13 minus T13. And finally T10 minus T10. What about over here? Here we have T21, and over here it must be minus T21. Here's T20. This is minus T20. And finally down here, what do we have? T30 minus T30. So it's antisymmetric, which means that when you reflect it about the diagonal, it changes sign. And antisymmetric also means that it changes sign when you interchange the two indices. Those are called symmetric and antisymmetric tensors. Okay. How many interesting components does a symmetric tensor have? Let's count them. The symmetric tensor has 4 diagonal components, 1, 2, 3, 4, and then how many off-diagonal components? There are, of course, 16 components altogether, but the component over here is not independent of the component over here. So really, the independent components, the number of numbers that you need to know, is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9? No. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 independent components determine a symmetric tensor. Okay? So what? So nothing. But how many an antisymmetric tensor? Well, for an antisymmetric tensor, there are zeros on the diagonal. So we can subtract 4 of them. Only this, 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 and this. Zeros on the diagonal, and the other ones off on the other half of the matrix here are determined in terms of these. How many is that? 6. 6. That's the number of components of the electric and magnetic field. Okay. That's the number of components of electric and magnetic fields. This is the only object that you can construct. The antisymmetric tensor is in fact the only object that has 6 components and which transforms, well, you could take 6 scalars. 6 scalars, or a 4-vector and 2 scalars would also have 6 components. But none of those correspond to the electric and magnetic field. The electric and magnetic field form an antisymmetric tensor. They form an antisymmetric tensor, and out of that antisymmetric tensor, we want to understand this equation here and how it transforms under Lorentz transformation. Now, it does transform in a complicated way, and that means that the electric and magnetic fields are going to transform into each other. I'm going to write down, we're going to finish now, I'm going to write down for next time, I'm going to write down the precise relationship, but we're going to derive this. We're going to derive this, but I'm going to write down the precise relationship between the antisymmetric tensor and the components of the electric and magnetic field. How do the components of the electric and magnetic field combine themselves together to make an antisymmetric tensor? So, we take our 4x4 matrix, which I'll draw some guidelines so that I know where the elements are. The zeros on the diagonal. The off-diagonal, I don't need to specify both above and below. Once I specify above, you can read off what's below just by changing the sign. And here I'm going to tell you what they are. This is 1, 2, 3, 0. 1, 2, 3, 0. X, Y, Z, T. This is the 1, 2 component. In the 1, 2 component, we put minus the 3rd component of the magnetic field, BZ. Let's see, we put the 3rd component of the magnet. In the 1, 2 place, we put the 3rd component of the magnetic field. In the 1, 3 place, we put the 2nd component of the magnetic field, the Y component of the magnetic field. And guess what goes down here? Down here goes minus the 1st component of the magnetic field. Right? So if we didn't have time, suppose we didn't have time, we only had 1, 2, and 3, then the antisymmetric tensor would only have 3 components. And those 3 components would be identified with the three components of the magnetic field. We're going to discuss this further, but for the time being, this is the setup for the way that the magnetic field enters into a antisymmetric tensor. Now,
Are those all minuses?
no, minus, plus, minus. We'll see why.
Are those supposed to be thought of as coordinates, like X, Y, Z, the components?
Yeah, this could be the z component. This could be the y component, or would be. This would be the x component. And then we would write x, y, z time. Okay. Is that what you meant? Yeah, okay. All right, now we have three entries over here, three more entries. Obviously, those three entries must have something to do with the electric field, and of course they do. Ex, Ey, Ez. Do I have the sign right? Yeah. Let's just put in what goes down here just to fill it out. We have plus Bz here, minus By here, minus Ex here, plus Bx here. Let's see. Minus Ey and minus Ez. So it's now got 6 independent components, and it fills out a 4x4 matrix, antisymmetric 4x4 matrix, with electric fields in the time slot here and magnetic fields in the space-space slots. The space-space components are magnetic fields, the space-time components are electric fields. Now, why is this? How did I know this? How did anybody know it? We'll come to that next time. They know it by fiddling around and trying to find a sensible relativistic generalization of this formula here. So the next time we'll work that out. We'll work out F equals ma for a particle in an electric and magnetic field, except in relativistic notation. Incidentally, this 4x4 matrix here is not usually called T mu nu, it's called F mu nu. I don't know the history of why F is called F, but I suspect it's Faraday. I suspect F stood for the Faraday tensor. And it's antisymmetric, and it's composed of the magnetic and electric fields.
So each of those elements is the strength of the field, the X, Y, or
It's the components of the field. The components of the field. Yeah. So here, let's just concentrate on the magnetic part of it here. Let's put a little fence around the time stuff and get rid of it for a moment. This now just constitutes a three-dimensional tensor, antisymmetric tensor. And let's write down the equation. This equation says that F12 is equal to minus Bz, or minus B3. 3 is Z. Next, F13 is equal to plus By. And finally, what's the last one down here? The last one is 23. F23 is equal to Bx. In fact, this is 3. Yes, minus B1, B2. Okay, now I can write this in a nicer form where you'll see the pattern. Let's write this one not as F13, but rather as minus F31. If I write this as minus F31, then I have that F31 is B2, and F23 is minus B1. What do I see in that form that I like about it? Let me show you how it works. Let's let's start with the equation F12 equals minus B3. And let's cycle from 1 to 2 to 3 in each spot. In each spot, the next equation, you go 1 to 2, 2 to 3, 3 to 1. And make a clock that goes around in a circle. 1, 2, 3, and let's proceed clockwise. All right, the next equation down, everything would cycle forward. So what would happen to the 1? Become 2. What would happen to the 2? 3. What would happen to the 3? Minus B1. What's the next one? 1, 2, the next one would be 3. F3, 2, 3, 1 equals minus 3, 1, 2. Well, with any luck at all, that will be exactly what we wrote here. Let's see, F12 is minus B3, F31 is minus B2. Don't worry about whether they're upstairs or downstairs, forget that. F23 is minus B1. So this has a very nice structure to it. The 1, 2 component of the tensor is the third component of the magnetic field. The 2, 3 component of the tensor is the 1 component, and it cycles. 1, 2, 3, 2, 3, 1, 3, 1, 2. So you can always remember, all you have to remember is one of them, and the others will follow just by cycling the numbers from 1 to 2 to 3. Now, the electric field is different. The electric fields E1 is equal to F10. E2 is F20, and E3 is F30. So the electric fields are vectors where you just ignore the time component here. And you see what the index structure is. E1 is F10, E2 is F20, E3 is F30. The magnetic field, a little more complicated. There's something you might notice. The magnetic field seems to have two identities. It has an identity as an antisymmetric tensor whose components are called F, and it has another identity as a kind of vector. Ordinary three-dimensional vectors. When I speak of vectors now, I'm speaking of three-dimensional vectors. It has an identity as an antisymmetric tensor in 3 dimensions, minus b, 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 minus sign here, and it has a second identity as a vector. That connection between antisymmetric tensors and vectors is only true in 3 dimensions. It is not something which is true in other dimensions. It's just an accident. Well, it's not exactly an accident, but think of it as roughly accidental, that if you take a 3 by 3 antisymmetric matrix, it happens to have 3 independent components. Those 3 independent components also happen to form an ordinary 3-dimensional vector. But if you have a 4 by 4 matrix, antisymmetric, it cannot be identified with a 4 vector. So we see that the magnetic field sort of has 2 identities. In one identity, it has 2 indices, and in the other identity, it has only 1 index. We're going to build, next time, out of this antisymmetric tensor and 4 velocities and 4 accelerations, 4-dimensional accelerations, we're going to build an equation which will recognize as having transformation properties that make certain that it's the same in every reference frame. That's our goal, to rewrite this so that it's the same in every reference frame. We'll have to modify it a bit. This is not quite right as it is. And when we modify it, it will form an equation which is the same in every reference frame. Yeah.
So was Einstein looking for this, the Lorentz invariant formulation of electromagnetism just on conceptual grounds, or did he have any empirical?
Say it again?
Was he doing that just on conceptual grounds?
Yeah. Yeah. He had a suspicion that the laws of nature ought to be the same in every reference frame. This was a matter of intuition to him, or a matter of conviction. It, of course, Also had a good deal of experimental support, the fact that the speed of light was the same in every reference frame as far as it was measured, that nobody could detect using light the motion of the Earth through space. But I don't even think he knew that. I don't know if he knew it. He said he didn't know it. I don't know if he knew it or not. But he himself, according to his own description, was more influenced by the principle of relativity, and he could not make these equations be the same in every reference frame, not without doing something to mix E and B up, and even that wasn't enough. He had to mix up the components of the velocity. Eventually, he had to figure out special relativity. He did not actually write his equations in four-vector notation. He just put in all the various extra gammas and functions of velocity. But what he was doing was basically making sure that the equations were the same in every reference frame by making them into four-vector equations. It was Minkowski who really put together the four-vector idea and rewrote the equations in a four-vector notation. But Einstein was more or less somewhat clumsily going about writing these equations in a way that they would go from one frame to a next by some systematic transformation properties, and they would always be the same in all reference frames. So yeah, it was essentially a conceptual guess on his part that Maxwell's equations, together with the Lorentz force law, should be the same in every reference frame.
So you had to learn tensors for general relativity. Did you feel silly about special relativity then? No.
At first, I don't know a hell of a lot about the history of it. And you know, history is always in the eye of the beholder, and what people say is not always exactly what happened, so I don't really know. But I think according to his own writings, he at first did not like Minkowski's ideas. He didn't like the idea of four-dimensional geometry at first. It didn't take him long to catch on, but at first he simply wrote everything out in sort of clumsy, brutal form, and had a hard time adjusting to the neater notation. That's what he said anyway.
Minkowski come up with this within about a year or so?
I think it was 2 years. I think it was 1907, if I remember. You know, yeah, things move slower at that time than they do now. That's pretty fast, yeah. Yeah. Well, I think if it was today, it would have happened much faster, but...
Was he Minkowski a mathematician or a physicist?
Well, I'm not sure that people necessarily distinguished at that time. And I don't know that he was, that he contributed much else to physics. Not that this wasn't enough. I mean, this was a huge amount to contribute. But I don't know what else he did. There was no long history of famous papers by Minkowski. This was essentially his high point.
Am I correct? That was Einstein, but am I correct?
I really don't know. Do not know. Was he affected by Lorentz? Don't know. I think probably yes. Was he affected by Fitzgerald? Who knows? I don't know. The one thing I know is you don't trust people when they give answers to those questions. They don't remember.
So do you know if the tensor transformation of E and B was in his first paper in 1907?
No. It was in Einstein's paper in 1905. Yeah, but he just had it, written out by hand. When Maxwell wrote his equations, he wrote every single equation: the x component, the y component, the z component. How many of them are there altogether? Let's see. There's E dot. There's one equation for E dot. That's 3 equations. 6 equations. 7, 8 equations. 8 equations? I think 8 equations altogether. No. There's more than that. Wait a minute. Sorry.
Vector notation was invented in 1880.
I don't know. So this was 3, 6, 8 equations, and I think he wrote out all the x component of this, the x component of this, 1, 2, 3, 4, 5, 6. Yeah, he wrote down all 8 equations and never put them together into some nice symbolic form. Well, Einstein was doing essentially exactly the same thing in space-time. He was just writing everything out and sort of doing it by trial and error. You get the feeling when you read the paper that he did it by trial and error rather than anything as systematic as 4 vectors. It was Minkowski who understood the 4-vector idea. So it was a hit and miss for Einstein with some good intuition about okay, let's next time we'll come back and we will work out the Lorentz force law as modified by Einstein and Minkowski.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.